Dear students, let us we start today about a topic, Werner's theory of coordination compounds. So before to start with a topic, Werner's theory, let us we know the difference between coordination compounds and the double salts. A coordination compound contains a central metal atom or ion surrounded by number of oppositely charged ions or neutral molecules. These ions or molecules is rebonded to the metal atom or ion by a coordinate bond. When two salts in stoichiometric ratio are crystallized together from their saturated solution, they are called the double salts. The examples of the double salts are the ferroammonium sulfate, commonly called Morse salt, then potash alum KCl MgCl2.6H2O. This is a carnallite, and the potash alum is K2SO4.Al2SO4 thrice 0.24H2O. The examples of coordination compounds are potassium ferrocyanide, Cupramorium Sulfate, hexamine cobalt 3 chloride, and so on. Coordination compounds do not dissociate into simple ions when dissolved in water, whereas the double salts, they dissociate into simple ions when dissolved in water. Now, in the last class, we have studied about the various terms of the coordination chemistry. Now, let us we study these terms taking an example of potassium ferrocyanide. In case of potassium ferrocyanide, Fe in +2 state is a central metal ion. Cyanide is a ligand. There are 6 cyanides attached to the central metal ion, and the 6 becomes the coordination number. FeCN6 carrying -4 charge is called a complex ion. This charge is balanced by 4 potassium ions, and these ions are called the counter ions. Similarly, in case of the COCl2NH3 4 times Cl. In this case, the cobalt in +3 oxidation state acts as a central metal ion. Chloride ion and ammonia both together forms the ligands. So the total number of ligands is 6. So the 6 becomes the coordination number, and COCl2 NH3 4 times having a positive charge called the complex cation. This cation, the charge is balanced by 1 chloride ion, and that chloride ion is called ionizable ion. Now, about the Werner's theory, to start with, let us we study about the scientist Alfred Werner. Alfred Werner is from Switzerland and was born in 1866 and died in 1919. At the age of 26, that is in 1893, he proposed the coordination theory. Today, Werner is called the father of coordination compounds. He won the Nobel Prize for Chemistry in 1913. So, he did work on addition of 6 moles of ammonia to cobalt chloride, conductivity studies, precipitation with AgNO3. Now, let us we study about the Werner's theory of coordination compounds. The main postulates of Werner's theory are: every central metal ion in a coordination compound possesses 2 types of valencies, namely primary valency and secondary valency. The primary valency is ionizable and is non-directional, whereas the secondary valency is non-ionizable and is directional. In modern terminology, the primary valency corresponds to oxidation state and the secondary valency corresponds to the coordination number. The primary valencies are always satisfied by negative ions, but secondary valencies are satisfied by either negative ions or neutral molecules. In certain cases, negative ions may satisfy both primary and secondary valencies. Every metal ion has fixed number of secondary valencies. These are always directed towards the fixed positions in space, which leads to definite geometry to the compound. If the compound is having coordination number 6, it gives octahedral geometry. If the compound is having coordination number 4, it gives either tetrahedral geometry or square planar geometry. Thus, the secondary valencies directed determine the stereochemistry of the complex. Now let us study some of the applications of Werner's theory to the coordination compounds. Taking first example as potassium ferrocyanide. In case of potassium ferrocyanide, potassium valency is +1. Since 4 potassium ions are there, therefore the charge becomes +4. Iron valency is +2. Cyanide valency is -1. 6 cyanide ions are there, hence it is -2. Therefore, +4 +2 -6 total becomes 0. Always the compounds should have a total charge 0. Therefore, potassium ferrocyanide is also having a charge 0. In this case, primary valency of iron is +2, secondary valency is 6. Here, among the 6 cyanide ions, 2 cyanide ions satisfies both primary valency and secondary valency. This compound exhibits octahedral geometry. Taking another example known as Cupramorium Sulfate. Here, valency of copper is +2, valency of ammonia is 0 because it is a neutral ligand, and the oxidation state of sulfate ion is -2. Therefore, +2 + 0 -2 is equal to 0. Therefore, the cupramonium sulfate is having the primary valency of copper +2, secondary valency 4, and ammonia is a neutral ligand, and this compound exhibits square planar geometry. Coming to some of the complex ions, FeF6 3-. It is a complex ion. In this complex ion, the iron valency is +3. 6 fluoride ions are there. Hence, the charge becomes -6 +3 -6, and the charge becomes -3. This -3 is written on as a charge of complex ion. Here, primary valency of iron is +3, secondary valency is 6. Among the 6 fluoride ions, 3 fluoride ions satisfies both primary valency and secondary valency, and this complex ion exhibit octahedral geometry. Coming to another example, PtF6 having -4 charge. Here, oxidation state of platinum is +2, 6 fluoride ions charge is -6, +2 -6, the charge becomes -4. That's why the PtF6 complex is having a charge -4. Here, primary valency of platinum is +2, secondary valency is 6. Among the 6 fluoride ions, 2 fluoride ions satisfies both primary valency and secondary valency, and this complex exhibit octahedral geometry. Coming to the another complex cation, that is COCl2 NH3 4 times having plus charge. Here oxidation state of cobalt is plus 3 and valency of chlorine is minus 1, 2 Cl are there, hence minus 2. Ammonia is a neutral ligand, so therefore plus 3 minus 2 is equal to plus 1, and this plus 1 is written as a charge of this complex ion. In this case, primary valency of cobalt is plus 3, secondary valency is 2 chloride ion and 4 ammonia, it is 6. Among the two chloride ions satisfies both primary valency and secondary valency, and this complex cation exhibit octahedral geometry. Coming to the another example, ZnCl4 2 minus. Here oxidation state of zinc is plus 2 and 4 chloride ions are there. The charge becomes minus 4. Plus 2 minus 4 is equal to minus 2. That's why this complex is having a charge 2 minus. Primary valency of zinc is plus 2, secondary valency 4. 2 chloride ions satisfies both primary valency and secondary valency, and this compound exhibits tetrahedral geometry. Let us take another complex compound, that is K2NiCN 4 times. In this case, potassium valency is plus 1, 2 potassium is plus 2, nickel valency plus 2, 4 cyanide ions minus 4, so the total it becomes 0. Therefore, this complex compound, it is a complex compound but not an ion. Here primary valency of nickel is plus 2, secondary valency is 4. Among the 4 cyanide ions, 2 cyanide ions satisfies both primary valency and secondary valency. This compound exhibit square planar geometry. Here I have shown the geometry of octahedral, tetrahedral and square planar. In case of octahedral geometry, the bond angle is 90 degree. And in case of tetrahedral geometry, the bond angle is 109 degree 28 minutes. In case of square planar complexes also, the bond angle is 90 degree. Now we'll study now explanation of Werner's theory taking cobalt amine complex as an example. Werner explained his coordination theory based on this compound. He took COCl3 6NH3 as a compound, and this compound is having orange color. And here the cobalt is a central metal ion and its oxidation state is plus 3, and which becomes the primary valency of the cobalt. Ammonia is a ligand and the 6 ammonia molecules are attached to cobalt, and this ammonia, the 6 ammonia becomes the secondary valency of the cobalt. The coordination number and the CONH3 6 times 3 plus is a complex ion. Primary valency of cobalt here is 3 plus and secondary valency is 6. Here chloride ions are ionizable and ammonia is non-ionizable. Around the cobalt 3 ion, 6 molecules of ammonia are directed towards the 6 corners of octahedron to form octahedral geometry. This compound in solution gives 3 chloride ions and a complex ion. So totally it produces 4 ions. The amount of AgCl formed from AgNO3 corresponds to 3 chloride ions. He also used another compound COCl 3.5 5H2O. This compound is purple in color. Here cobalt is a central metal ion and 5 ammonia and 1 chloride ion acts as ligand. Coordination number becomes 6 and the complex ion is CONH3 5 times Cl carrying 2 plus charge. Primary valency of cobalt is 3 plus and secondary valency is 6. The 6 is 5 ammonia and 1 chloride ions. Chloride ions within the square bracket satisfies both primary and secondary valency. Hence, it is non-ionizable. Around the cobalt 3 ion, 5 ammonia and 1 chloride ion are directed towards 6 corners of octahedron to form octahedral geometry. In solution, this complex gives 2 chloride ions. Therefore, the amount of AgCl formed from AgNO3 corresponds to 2 chloride ions. Coming to the third compound, COCl3.4NH3. This compound produces the two types of isomers, cis isomer and trans isomer. Cis isomer is violet in color and trans isomer is green in color. Here the central metal atom metal ion is cobalt in +3 state and both chloride ions and the ammonia acts as a ligand. Now the solution of this gives only one chloride ion. Therefore, the amount of AgCl formed from AgNO3 corresponds to 1 chloride ion. Lastly, we take the COCl3.3NH3. In this, the coordination number of cobalt is once again +3, secondary valency is 6, and here 3 ammonia and all the 3 chloride ions satisfies the secondary valency. All the chloride ions satisfies both primary valency and secondary valency. Therefore, this compound will not give any chloride ions in solution. Hence, it is a non-ionizable compound. The complex exhibits octahedral geometry and it does not undergo any ionization. Hence, this compound does not give any white precipitate with AgNO3. Here, this table shows the earlier explanation. COCl3.6NH3 is an orange compound and it produces totally the 4 ions. Among the 4 ions, 3 are the chloride ions. Similarly, the second one, COCl3.5NH3, which is purple in color, produces totally the 3 ions. Among the 3, 2 chloride ions and 1 complex ion. So, COCl3.4NH3 produces the two types of isomers. Here I have given cis isomer and trans isomer. Cis isomer is violet in color and trans isomer is green in color, and their modern formulas are also given. This gives the structure of CONH3 4 times Cl2. Here both the chloride ions are with respect to cis position in the first case, which is the red form or the violet form, and in the second gives the 2 chloride ions are trans to each other, which is a green form of this complex explained by the Werner. Lastly, let us study about the merits of Werner's theory. Werner could explain the existence of complex ions satisfactorily. He could differentiate between primary and secondary valencies. The theory explains the geometrical shapes of complex ions satisfactorily. The demerits of Werner's theory includes the theory is not based on electronic theory. It cannot explain how a negative ion can satisfy both primary and secondary valencies. Students, let us you learn the Werner's theory in detail and try to understand the merits and the demerits of the theory. Thank you.